It will take a couple of seconds. Okay, we are live. Hello everyone, this is our fourth live stream and we have Soham Tiwari with us today. Soham has majorly worked in NLP till now, and he has worked and submitted on two research papers, one involves multimodal analysis of text data to classify tweets, uh, to classify different forms of hates and biases and other negative emotions in tweets, and the other involves building a data set from scratch which contain sexually harassing tweets, and finally using the same to deploy sexual harassment detective work. Today, Som will be presenting a paper, time series forecast for classification and feature extraction, and we'll see why is he interested into this domain and what are the applications, and how is like this paper from 2013, how it can actually help us even in 2021. So with that, I'll hand it over to Soham. Soham, you can go.
Thank you, Sahil. I'd like to apologize for in the beginning only because unfortunately there's some construction work going on a Sunday today, so there might be some background disturbance. However, let's get started.
Soham, you can request for access and
Yeah, yeah, I have. Okay. Right. So today I wanted to present you all this paper which actually modifies the popular random forest algorithm, which is a popular machine learning algorithm for the particular application of time series classification. So what are the advantages, number one, of using a machine learning algorithm for time series classification? So as we know that the popular state of the art today, which is being utilized, is usually involves heavy neural networks. For example, sequential networks such as LSTMs, BiLSTMs, and maybe even better and much more deeper sequential networks. However, we do not, if we wish to deploy any such ML application, which can suppose work on a smart device or on a portable device, we do not have the luxury of, like, alone GPUs, we do not even have the luxury of powerful enough CPU. So we need to look at compute efficient algorithms such that we can actually perform like ML predictions, or in this case, time series classification on devices which have low compute resources. So like problems which can come under this domain, for example, if you have a smartwatch which can monitor your pulse and it can automatically tell you what is the condition of your body or the condition of your heart, and if it can tell you what diseases is currently your heart is suffering from. So that's one potential application. Then other applications include, for example, if you want to deploy weather monitoring bot or balloon, and you want to, so basically what you can do, you can deploy a bot which can go into the atmosphere, and it has a few sensors attached to it. And then maybe we can also have a time series classification model deployed on that chip, such that it can monitor the pressure differences or any other weather data, and it can accordingly make predictions with whatever accuracy which we can extract from the low compute model, and can preferably make predictions about the incoming weather, report back the same towards a central server. So these are the multiple applications which one can look at. For example, what one can utilize for time series classification on low compute devices. So let's start. Okay. So first and foremost, a time series forest is a random forest algorithm. It's just that the data has been modified, or the temporal data has been modified such that it can actually work with an ML algorithm which is more suitable towards tabular data. So as you can see, it's an ensemble method, which actually implies that you have multiple models and you aggregate together the predictions of multiple models, and then using the for example, one method is you can take the majority predictions and then classify a particular time series, but there are different ways you can actually decide on that. And then again, so but as most those who are aware of, okay, those who aren't aware of random forest algorithms, so the random forest basically constructs multiple trees you can imagine for a tree, you can imagine that it is in fact a binary tree where the input data is fed into the network from the topmost node. And then on the basis of certain thresholds and criteria, your, your input data are then sorted into different children nodes. So again, and this is one such tree. And in a random forest, you're sort of using the ensemble method for multiple trees grouped together. So in this paper, the authors proposed that the TSF, or the time series forest, will employ a combination of entropy gain, which is a popularly used metric to decide on what basis the nodes should be split in, the data should be split at the nodes, and a novel distance measure, which I will explain on ahead. And if we can, so okay, before I explain this, so why TSF and why not experiment with other machine learning algorithms for time series classification? So the thing is that the other actual alternatives, they include rice, diesel, and k nearest neighbors with dynamic time warping. So unfortunately, I will not be able to dive deep into all the algorithms which are listed. However, I can show you one such algorithm which is quite easy to understand, and it is actually known as k nearest neighbors with dynamic time warping.
You want me to show the?
Yes, please.
Yeah.
Thank you. Right. So this is another algorithm which before TSF came along was extremely popular for using ML, like it's an ML based algorithm for time series classification. So the logic or the intuition behind it is that you're effectively using the k nearest neighbor algorithm, and you're sort of going to compare, or you have trained the k nearest neighbor algorithm on different time series sequences, and then on the input sequence, you basically want to compare how similar the input sequence is how it's similar it is to the already trained input sequences. So, however, one major limitation of the normal k-nearest neighbor algorithm is that the metric used for comparing similarity is not sufficient in the case of time series sequences. The most popularly used metric is actually the Euclidean distance, or for example, in simpler words, it's basically the distance between 2 points on a graph, which is square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. So if we use that kind of similarity metric while trying to compare the similarity of two time series sequences, we may not obtain the most optimal results. As you can see, using the Euclidean matching for these two time series, just from the visual, just from a visual inspection, we can observe that the blue time series sequence is extremely similar to the red time series sequence. The only difference being that the blue time series sequence is just a bit more elongated, or it's longer. And if we decide to use the Euclidean matching, the Euclidean matching will actually use the corresponding data points and then compute the Euclidean distance between those data points. And as a result, the Euclidean matching may report that these two time sequences are not similar. Because, for example, if we just even consider the first initial data points, so the distance between the point 0 on the blue line and the point 0 on the red line, it's extremely large. So that would make the k-nearest neighbor algorithm think that these two sequences are in fact not similar. Whereas the ideal situation would have been that we should actually compare the point 0 on the blue line with, for example, this fifth or sixth point on the red line. So these 2 points are extremely similar. And this kind of skewed comparison should take place along the entire time series sequence. And only then will it actually yield that these two sequences are in fact similar. So dynamic time warping is just a complicated name, but which achieves the same thing, where we are in fact trying to map distant time series sequences along similar data points at different points of time. For example, the data point at timestamp 0 is being compared with the data point at, I think this is, let's just say any arbitrary value, let this be data point at 10. And in this way, the k-nearest neighbor algorithm is able to better classify input time series sequences because it is in fact using a dynamic time warping matching algorithm. So if I just go to explain this algorithm, right? So it's a bit more. Yeah, this is the algorithm. So we're starting off with an empty matrix, and the dimensions of the matrix are dependent upon the size of the individual time series sequences which we're comparing. And we initialize all of them to infinity except the first element in the matrix, which is 0, 0, and we're setting it to 0. And then what we do basically iterate over all it's an n square loop, and we iterate over all the data points, and we're finding out the distance between a data point on suppose sequence S and the jth data point on sequence T. And then we're using this logic to actually update the element at the I comma jth index. So before I move ahead, so basically what the DTW I comma j, it indicates, as it has been mentioned, it is a distance between the sequences. For example, the first I indexes of sequence S and the first j indexes of sequence T. And it's sort of the distance has been computed using the best alignment. So if I show you the graph again, right, this matching, yeah, this matching is happening dynamically as you iterate through all the loops. So, for example, since it's happening dynamically, it's going to find out the minimum distance between, for example, the first I data points on this blue line and the first j data points on this red line. And the algorithm then proceeds with this. And finally, when the algorithm is done computing, so the last element of the matrix, which is DTW index n and index n comma m, so that will effectively contain the minimum distance between those two time series sequences. So that is the beauty of this algorithm, that it is not even constrained by the input time series sequences do not even have to be of the same length. So the QnA algorithm, before time series forest came along, that was kind of the best machine learning algorithm for time series forests. However, with the introduction of TSF, things started changing. Yeah. So as you can see, one of the biggest advantages of TSF is that it has a linear computational complexity. Which
Give me a second. I have to change it on the software. Yeah, you can continue.
Right. So the TSF has a linear computational complexity, which in basic term implies that for example, if the length of the time series, the number of sequences in the time series increases from 100 to 200, the increase in the time taken to process that sequence will also be 100, since the difference was 100 in the input data. So that's what it implies, that it is linear. But it can also be right now assume that the multiplication constant, like it would actually be n times the difference in the distances. So it can effectively be implied that for an increase of 100 data points from the first data sequence to the second data sequence, my time complexity or the time taken to process that sequence will increase by multiplication constant 2 into the number of and the difference in number of data points, which is 100. So it will effectively increase by 2. And then they've also introduced different forms of visualization, how important certain features are, but we'll tackle that as we proceed. Right. So first and foremost, the initial, if I ask anyone, like a person who's first thinking about using ML algorithms for time series data, so they would just maybe start off by considering each and every time point as a feature and just use a regular classifier such as nearest neighbor algorithm with Euclidean time distance, or maybe if they know more about it, they can even use dynamic time. However, this such an approach will not prove sufficient because the for time series classification mainly, it's important to have a sense of both the local trends as well as the entire global trend. So if we consider such kind of an approach, we're considering each time point as a feature, we will not be able to obtain a desired effect. So that's why the approach which in such algorithms is utilized is actually computing temporal features. So which in basic terms, it implies that you are taking subintervals of a long time series sequence. And then for that subinterval, you're going to compute a few features. Those features can be different. They can be spectral features. So algorithms which I listed previously, such as Rise and Basil, they actually they make use of spectral features, whereas time series forest currently, like because of its simple nature, it's only making use of statistical features. For example, if we take into consideration a small subsequence of 10 data points out from a long subsequence of 100. So on that subinterval or that subsequence, we're going to compute, for example, simple statistical values such as the mean and the standard deviation of that interval, as well as the slope. I'll move on. So I'll just quickly move on to the different sections of the paper. This was covering the basic introduction of what this paper proposes. Okay, just to explain this graph. So right now we can save multiple time series sequences, and it's also we can one standout point is that for each of the red graphs of the red time series sequences, the the deviation is occurring between 200 to 400, but at different time points. They're not exactly happening at the same time. Therefore, we use temporal features. So it depends upon also on the interval length, but using temporal features, we can maybe then identify if we suppose use that, if we use a temporal feature which is calculated over an interval of 200 to 400, and we build a classifier on that. So the temporal feature or the temporal feature, which is the standard deviation for an interval of 200 to 400, it will say that for classes, time series sequences of classes 2, it's the standard deviation for in 200 to 400 interval should be suppose 10. Whereas similarly, all those time series sequences which belong to class 1, the standard deviation in 200 to 400 should be 0. So that is an example or just a very basic intuition as to how these temporal features can be effectively used to classify two different time series sequences. So here I just displayed or I just explained to you all how it can be done using the standard deviation temporal feature.
So, can you again explain what the graph is representing?
Okay, right. So the graph is basically these are different time series sequences themselves. So if you can see the thickness of the blue line right now, I'm not sure if it's representative of anything, but we can consider them to be separate time series sequences which belong to class 1. Whereas the red lines, they're actually time series sequences which belong to class 2. So our aim is to build a model which can successfully distinguish between sequences belonging to class 1 and sequences belonging to class 2. So just by visual inspection, we can see that using the standard deviation feature. In the standard deviation feature over the interval 200 to 400, the model can learn to classify that over the interval 200 to 400, the sequences which have a standard deviation of suppose greater than 5, greater than equal to 5. It's just an arbitrary number. It's nothing. It's nothing particular. An arbitrary number. So those sequences which have a standard deviation of greater than 5 in the interval 200 to 400, they can be classified successfully as class 2. Whereas those which have lesser than 5, they can be classified as class 1. So this is just to portray different time series data.
Okay, understood.
Does that make sense?
Yeah, it does.
Okay, so the related work. So time series classification methods can be broadly classified into instance-based and feature-based. So the initial algorithm, which I explained to you all, which is k-nearest neighbors with dynamic time hopping. So that is effectively an instance-based algorithm where we're not computing any features of the time series sequence, but rather we're rather comparing time series sequences or each time series instance as a whole with other instances which the model has been trained on. So that is an instance-based algorithm. Whereas time series forest, the algorithm which we're exploring right now, that is a feature-based method, where we're in fact computing a few features. That's an intermediate step. We're computing few features of the time series sequence, and then we're feeding those time series features into the random forest algorithm to make our prediction and classify the input time series into one of the multiple classes. So as it's stated among instance-based classifiers, we have nearest neighbors algorithms with Euclidean distance and with dynamic time warping, etc. They're also just restating the fact which I stated earlier, which is dynamic time warping performs much better than Euclidean distance because of better mapping between two sequences which when they're being compared. Right. One of the major limitations of instance-based classifiers that although they can be accurate, they provide very limited insights into on what basis, in fact, is the temporal or the classification of the time series is happening. It's more like, in fact, just because these two input time series sequences are similar, you're classifying that into class A. So it's more along the lines of transductive learning rather than inductive learning, where we haven't induced anything from the training data set. We're just comparing patterns. So that is why instance-based classifiers cannot really be useful in the long run because they haven't really induced any trend or any information from the training data. Whereas on the other hand, feature-based classifiers, as I said, since they make use of temporal features, they're in fact actually inducing or learning trends or learning knowledge about the input training data and using that to make predictions rather than just comparing similarity between two input instances. Feature-based classifiers, so the flow can be broken down into two steps. First is defining the temporal features, like what features do we want to compute over a particular time series. And then we're training the classifier on the temporal features which we have computed. Some other related works involve computing boosted binary stubs, which basically implies they're using algorithms which are along the lines of any boosting algorithm such as adder boost or etc., where we are in fact using stumps. So what stumps basically mean is that instead of having a very deep random forest, it's just a two-level random forest where we have one parent node and two children nodes. That's why the name binary stumps. And boosted, in fact, is just a mechanism where it's a form of ensemble learning where you're feeding, for example, you're feeding input data into the first boost binary stump. And the binary stump will get a few predictions right, and a few predictions wrong. So the predictions which are wrong from the first stump, that will be fed into the second binary stump. And that second binary stump will be trained to properly classify the misclassified samples by stump one. And this sort of feedback system can be done over multiple stumps. So that is just the basic intuition of what boosted binary stumps are. So that is another approach which had been explored earlier for this kind of a problem. Right. And another important, right, within decision trees itself, even though work has been done on using decision trees for classifying time series data, one of the major limitations, in fact, is that the decision trees, as I explained earlier, they split the input data into either of the multiple children nodes. So, but how to decide which is the best split for the input data? So earlier related works, they mainly use class-based measures, which I will explain ahead. But they only relied on class-based measures to decide which will be the best split for the particular node. But I will explain as to what this paper is doing different. And other time series algorithms involve using shapelets. So time series shapelets are basically they're just again sub intervals of the entire time series sequence, and they're doing instead of comparing entire sequences in like an instance-based classifiers. They're rather doing some form of computation on the subsequences of that text. So these are just a brief overview of the um, different related works which had been done in this field. So let's focus on this paper on the time series forest. So as I said earlier, this paper introduced or proposed to use very simple statistical features to be computed for each subinterval. So the features are the mean. So F1 indicates the feature number one, which is the mean over the standard over interval. F2, which is the standard deviation that indicates the standard deviation of the particular interval which is being monitored, and the slope. So the slope, in fact, is actually of the best fit line. So if we consider a linear regression model, so the aim of the linear regression model is to actually compute the best fit line along. Suppose you have a trend on your when you plot the data, you can see there's a linear trend. So the linear regression, the aim of linear regression is to basically determine how you can model the equation of that trend, or how can you basically determine the slope and the intercept of that particular trend line. So the slope over F3 is the slope of the best fitting line, which is computed using linear regression. So these are the formulas for the metrics. These look intimidating, but are actually quite simple. So VI is basically while iterating over timestamps T1 to T2, what is the value of the input time series subinterval at time I. So VI is value at I between T1 to T2. And this, so basically we are just computing the sum of all such values in that time interval, dividing by the number of instances or number of data points in the time interval. So this is just arithmetic mean. And this is the formula for computing the standard deviation, which is the square root of the variance. And here it's basically the value at a particular data point minus the mean which we computed earlier. So the square of that, and then we are computing the sum of all these values. And we're dividing that by the number of data points in that interval, and we're computing the square. So that gives us the standard deviation. However, when T2 is equal to T1, explicitly defining to be zero. Otherwise, if T2 and T1 were equal, this would have been zero. And then the standard deviation would have been infinity, which is not desired. And similarly for beta hat, the slope. Beta hat is just the slope of the least square regression line when T2 is greater than T1. And if it is T2 is equal to T1, it's just zero. That's just the basics of it. Right. So what this paragraph is telling us is that the interval feature space is supposed to be very large. It is of the order of m square, where m is suppose the number of data points in an entire time series sequence. So for example, if the time series sequence is 10,000 data points long, so that's 10 to the power 4. So according to this, our interval feature space will be very large, and it will be of the order of 10 to the power 8, which is huge, and we'll obviously have to do some form of dimensionality reduction. So that's why they're proposing, it is briefly stating that they think that using only intervals of length, which are powers of 2, should reduce the feature space to m log n. And another strategy, which is that they employ the random sampling strategy, which I'll explain further. But basically, it means that we are just instead of considering all the features in the feature space, you consider only a few randomly sampled features in this feature space to compute the split. And that reduces the time complexity to a linear one at each tree node. Now the splitting criterion. So as I said, in a time series tree, if you can visualize it as a simple binary tree, where the input data at the parent node has to be split into one of the two children nodes, which is the left node or the right node. But on what basis do you actually decide which input data will go into which node? So that's what is being defined over here. We compute a particular threshold. So this, I'll call this notation is actually tau, but I'll call this threshold. Like I refer to it as the threshold. And f of k. So f of k is just the general value. K can vary from 1 to the number of features which you have decided. But K, the upper limit of K in this particular paper is 3 because you only have 3 computed features. So what we're doing is we're basically whatever feature value we've computed for the interval T1 to T2, we're going to compare that with the threshold. So I'll explain how the threshold is defined ahead, what the paper proposes. But we're going to compare that with the threshold. And if the value computed of the feature value is less than the threshold, it's going to be sent to the left child node. Otherwise, it will be sent to the right child. So this is just a basic if-else condition.
Okay, so the FK would be F1, F2, F3, which is mean, standard deviation, and the slope respectively, right?
Yeah, that's right. So basically, even while splitting, right now they have just mentioned the single criteria. But even while splitting at a particular node, the algorithm might, instead of rather relying on only one particular feature, it can even rely on multiple features. So if on a particular T node, the algorithm has been trained and it is learned that at that particular T node, the mean for the input time interval should be suppose less than 0.5, and the standard deviation for that time interval should be greater than 0.5. So if this is being satisfied, you can go to the left child node, and if it isn't, you can go to the right child.
Okay.
So that's just the basic intuition of what is happening at each and every T node. And then similarly, this is just the set of values for the interval T1, T2, where n, so n is basically a variable which determines training instances at the node, and T1, T2 is the sub-interval at the node. And K implies which feature it is. So K will range from 1 to 3, and N ranges to 1 to N, which is the number of training instances at that particular node. Right. So one basic approach to computing a good threshold is in fact just to sort all the feature values for all the training instances and then select the best threshold from the midpoints between pairs of consecutive values. So, but however, this isn't a good approach. What would be a better approach is that you consider a set of candidate thresholds, not a single threshold. But so for a particular type of feature K, let's say the slope, we're considering, we're first of all going to find out what is the minimum possible uh, value for the slope at that node for any input data point, for any input instance, and similarly the maximum possible value for the slope feature at that node. And our aim is to determine the midpoint of these, or more specifically, you can either use the arithmetic mean, or you can even use the median at this point to split your entire input sequence into two equal width intervals. However, right now, as I said, I just took one, but we have multiple candidate thresholds. So candidate threshold is just a term where they can be potential threshold values. So they're in the race to be decided. Yeah, for example, I have 0 0.5, 0.25, 0.75. So these are potential threshold values. But again, so out of these, which particular threshold value will be selected? That is effectively determined using the different measures, which are, and like for example, as you can see on screen, entropy is one such measure. But the paper proposes a modified measure, which will be better approach to decide which threshold to use. And in their implementation, they have fixed the number of candidate thresholds. So this is not K. Unfortunately, I've forgotten the name of this notation, the Greek notation, but it is fixed to be 20. So the number of candidate thresholds will not exceed 20, and it will not even be less than 20. And the best threshold is then selected from these candidate thresholds using different methods. And here it is stating that the splitting criterion is needed to be defined to define the best split. So S is the notation, S star is a notation which indicates what, it's just assume that we have already computed the best splitting criteria, and that is being referred to as S star. So one such splitting criterion is entropy. So what entropy basically implies is that at that, first of all, it's a class-based metric. So what does class-based imply? It means that if your classification data set has multiple classes, so it's going to define the entropy on the basis of the purity of classes at that node. And what do I mean by purity of classes? Suppose you have two classes as an example. You have only two classes in your entire data set. So if at the node you have all classes, all the input nodes to belonging to one particular class. So in that particular node effectively becomes a leaf node because you do not really need to do any further splitting. Because at that node you're receiving uh, nodes of the same type itself. And we have finally reached our goal that we want to build a classifier that will give that one particular node will give us all the sequences which have been classified as class one. The classification might be incorrect completely. So the purity at that node, even though it might be 100%. For example, all the input classes arriving at that node are, for example, belonging to class 2, but are classified incorrectly classifying them as class 1. The entropy or the purity at that node will still be 100%. It's not considering the accuracy as much as what is the proportion or the distribution of classes in that particular node. So the entropy gain is basically the difference between the weighted. Okay, in simpler languages, you're going to calculate the entropy at the children node, at the child nodes, and the entropy of the parent. And the entropy gain is the difference. Suppose the formula is entropy of the left child node plus the entropy of the right child node minus the entropy of the parent. However, here they also go for a step further by taking the weighted sum. So you may even give certain weights you give more weight to one child node compared to the other. So they've taken a weighted sum of the entropy of the child nodes minus the entropy of the parent. And the greater the entropy gain which we have. So that for a particular split. So when we're actually going to iterate through the different splitting criteria, the model will be focused on finding out the splitting criteria which will give us the greatest entropy gain at that node. And what is that? For example, at the input node of the parent node, you have 3 samples of class 1 and 3 samples of class 2. But at that node, the node is classifying, suppose class 1 samples, only class 1 samples to go into the left child, and only class 2 samples to go to the right child. So in such a scenario, the entropy gain would be the maximum. And that splitting criteria, which the model has found out for that particular split, then the model will then continue to use that splitting criteria only for further training. So that is how the splitting is defined at a particular node in a random form and in a tree. Yeah, so entropy values the usefulness of separating classes, etc. Right. Oh, one important point which I missed out. Time series sequences are generally very large. So right now, 10,000 data points is also not as big as a number, which is usually faced. Your time series sequence might be of the range of maybe 50,000 times timestamps or 50,000 data points long. So it can be even larger. So the point is, therefore, the number of candidate splits, because if you have a 50,000 long sequence, 50,000 point long sequence. So in that, right now we have only 3 features, but we can have many more features for that 50,000 long sequence. And because of that, like as the number of features increase, the number of candidate thresholds or the number of candidate points on the basis of which you want to split the data, that will also increase a lot. So that's the number of candidate splits can be large. So therefore, we need to consider we cannot only rely on the entropy metric, because there might even be cases where the entropy gain is maximum when considering the split on the basis of the slope, and also at the same time it is maximum considering the split on the basis of the mean. But how do we decide between these two splitting criteria? So the authors suggest another criterion, which is known as the margin. So the margin is basically, as the name implies, what is the distance or the minimum distance between the lowest, how do I say this? So right, so over here is the threshold, and you want to for all the data point, for all the data instances which are there at your node, you're going to calculate the FK feature value for that node, for that data instance, and you want to find out the minimum difference value. So for example, if I say that for the split on the basis of the mean, the margin is only 0.1. But for the split on the basis of the slope or the standard deviation, both the entropy for both the mean and the standard deviation is the same. But the margin for the slope is much greater. For example, it can be 0.6. In that scenario, the slope, the slope metric, the slope feature will be a better splitting criteria because it will prove to be more robust in the future. For example, if we go for the less margin feature, which is the mean, it's just arbitrary. But if we consider the mean, who has the margin at 0.1, so if a random outlier just randomly pops into the data set, if the margin is very low, so the outlier might even fool the it might even fool the threshold. Like it basically might even fool the algorithm and get misclassified. Whereas having a larger margin helps us to basically establish a larger safe region, and it basically helps make the algorithm more robust. So the new metric which they propose is the entrance. And entrance is basically the sum of the entropy at that node, entropy gain at that node, and alpha. Alpha is just a multiplier for the margin. The greater the alpha, the greater the weightage the model is going to put on the margin. Or alternative method is that you can go on computing the entropy gain for each and every kind of splitting criteria which you have, each combination of splitting criteria which you have. And if there's a tie, then you find out among those tied splitting criteria which has the greatest margin. So the margin will then be used to break the tie. So correct, we have a visual representation. So you can see S1, S2, and S3. All of them have the same entropy gain. So how can we say that? For example, all the data points which are there on the screen. So you have two blue circles, two red rectangles,
Sorry,
and
what is S1,
two
S2,
green.
what is S1, S2, S3?
Yeah, S1, S2, S3 are basically just a visual representation of splitting criteria. So assuming that all these three data points are coming as input to the current node. So as the splitting criteria S1 will then split all the blue circles, will send all the blue circles to the left child and the red rectangles and the green triangles to the right child. So in that case, our entropy gain is there. For example, we are achieving pure, like 100% purity in the left child, but our right child is still impure. But if you observe all the three splitting criteria which have been generated by the model, we are achieving the same kind of entropy gain because if we consider splitting criteria 2, the splitting criteria 2 will send the blue circles and the red rectangles to the left child and the green triangles to the right child. So in that case, our right child has 100% purity, but the left child is impure with 50% purity. And similarly for splitting criteria S3. So S3 is also doing the same thing as S2, where the green triangles go to the right child and the blue circles and the red rectangles go to the left child.
So
The entropy gain, yeah.
We are assuming that the purity is the same only when the weights for the left child and the right child are equal. If it's unequal, then the purity will be different.
Purity is basically how do I
Right, because above you explained a formula where we have different weights for left child and right child, and in this case, in the first case, left child is pure and right child is not. But in S2 and S3, right child is pure and left child is not. So it will depend upon the weight also.
correct.
Will it be?
Right, it will depend on the weight as well. But right now, for this explanation, like it depends on it's more of an empirical basis what weight will be chosen because right now, like for example, right now I'm just considering an explanation where the
Weights are equal.
and the right equal weightage.
Yeah.
So considering also in this explanation that both the left and the right child have equal weightage. So right, so S1, S2, S3 will achieve the same entropy gain. However, why S3 will prove to be a better splitting criteria compared to even S2, like leave S1. If we just compare between S2 and S3, they both splitting the nodes in the same way. But S3 is a better splitting criteria because if we consider margin. So suppose if considering S3, a green triangle, sorry, a red rectangle. Yeah, a red rectangle pops up in this region. So because of this large margin, the splitting criteria ST will still send the red rectangle to the left check and not to the right check. However, if I use a splitting criteria S2, and a red rectangle appears in this region. So the splitting criteria S2 will then falsely send the red rectangle to the right side. In that case, our entropy gain takes a hit. So this is just an outlier which our model may fix. So that is why, as I explained earlier, considering the margin, like the greater the margin, the more robust our model will be. Like the greater the margin for that splitting criteria, the more robust the splitting criteria will be. Yeah. So this entire entropy gain in combination with the margin, that is called the entrance gain. Right. So these are just algorithmic representations of how to, for example, how to take the sample, like like what time sample to choose again. So depending upon the time complexity and different methods, like right now they're just going to out of the entire sequence of 1 to m data points. They're going to take a random sample or random interval of root m, size root m itself. And here this is just for loop for computing what is the interval going to be. Yeah. Oh, also, like as you can see, W is how does this? So just my basic point is that T1, T2. Right now we're taking interval lengths of root square m. So all the intervals which should be generated will be of length root m, or m is the entire length of the time series.
So,
and yeah, this is the
is that what gives the complexity, the algorithmic complexity of and like choosing just the root and number of points?
Yeah, that's it. You choosing the root m intervals of root m along with something known as random sampling, where this is the random sampling in case of which subinterval to select. However, ahead or the authors also suggest that instead of considering like generating splitting criteria for all features, like for all permutation and combinations, you're instead just randomly going to select the you're going to select, you're going to make random splitting criteria. So it's going to be arbitrary. So that also helps them reduce the time complexity. And it's actually, they're still able to achieve the same kind of very good performance and even better than the previous state of the art in low compute resources, which was KNNs with dynamic time. So this algorithm, suppose that we are getting a particular subinterval T1 to T2 using the sample function, which is defined above. And now the aim of this part is to actually compute the thresholds. So calculate threshold K, the set of candidate thresholds for each feature type. So what we're going to do is that for T1, T2. All right, before I just to clarify the notation. So T1, T2 is the set of all intervals of length square root m. And capital T1, capital T2. That's the set of all intervals. That small t1, small t2 is an individual interval of size square root m from the set which we computed earlier. So now what we're going to do is we're going to reverse over all the features which we have. So capital K in our scenario will be 3. And for tau in threshold K. So what we're going to do is we're going to compute the entropy, and E is the entrance for this kind of a split. And here we're determining if the entrance is greater than E star, where E star is just, like for example, if you want to compute the maximum, the simple algorithm, compute the maximum element in an array. So it's that kind of a logic. So the greater the entropy gain, then we make E star to be this current entropy gain. And we are also storing the threshold values in tau star and the intervals, etc. And we're storing the metric feature over which we're getting such a high. And these nested loops basically compute what would be the best splitting criteria. And if the first thing which they check is that if the entropy gain the maximum entropy gain is 0, then it's going to label it as a node and return. Otherwise, if it isn't, it's going to then split the input data into the left and the right side on the basis of the best splitting criteria, which has been computed above, like especially using these two lines of code, these two lines of the algorithm. And then since it's a recursive function, we're going to send the data left to basically call the function recursively again. So the name of this function is tree data. Correct. Also, one particular point which I forgot to visit is that the different types of features can also have different scale. For example, the mean values computed over all the intervals might be in the range of suppose -1 to 1. However, for example, the slope can be, for example, 5 to 10 maybe. So again, it can vary. So the scale in this case scenario differs. But right now, for the simplicity of this algorithm and simplicity of the paper, the authors have assumed that the scale of the features are also the same currently. Right. So as I said earlier, it's a top-down algorithm where you basically pass the entire data to the tree algorithm, and then whatever data you get, whatever input data is given to the first call of the tree function, you then generate square root of m sizes from the entire m sequence. This is the first call to the tree function. And then what you do once you decide the splitting criteria for the first, then you send the respective classified nodes to the respective nodes, to the respective suppose left and right child. And then at that node, this recursive function is called again, where at the where basically you're going to call again compute samples of subintervals of root m, and then go through the same procedure again. So that's why it's a top-down and recursive algorithm. And you start off by building the first node, and then you keep on building the tree downwards till you reach the leaf nodes where the purity is the maximum. Okay. So at each node, this is something I wanted to highlight. At each node, the random forest only tests root P features randomly selected from the complete feature set consisting of P features. So as I had explained earlier, this paper or this implementation of random forest is only considering of all the P features. Root P features only to decide the splitting criteria. So this is just an optimization to ensure that the algorithm is getting completed in O of m time only. And in each time series node, we only consider randomly sampling root of m interval sizes and root of m starting positions. So basically what implies is that if you have a sequence of size 100, so you're only going to consider 10 intervals of size 10. That's what this implies. And therefore the feature space. This is just an optimization made by the author to reduce the features of complexity to O. And in this case, the feature space complexity. And this is more or less the general gist of the time series forest. So as you guys would have observed, it's just a simple intuitive modification of the random series forest algorithm for time series data. So obviously the strength of the random series forest is in fact you classifying in simple words tabular data, where you have everything tabulated, where each row is a data instance and you feed that into the random forest classifier, it will give you prediction. However, the same approach, since we cannot use the same approach where we input the single instance of the entire time series into the classifier, we rather break down the entire time series into subintervals, compute the statistical features for that interval, and whatever features are then computed from that, we pass that to the random forest algorithm to make proper classifications. And that's why it's quite intuitive to understand as well, the time series forest types of classification algorithm. Right. And the time series forest is a collection of time series trees and predicts a testing instance to be, since it's an ensemble algorithm. So, and because it's an ensemble algorithm, you'll have multiple trees, and a testing instance, to the testing instance will then be classified as a majority class according to the votes from all the time series trees. Right. So over here, this is just an in-depth math of how the time complexity turns out to be O of n. Uh, yeah, I'm so sorry. Again, as I said, we already on the Sunday, the construction is still going on in my premises. But yeah. Anyway, so this is just uh, a little bit more in detail mathematics as to how the complexity turns out to be of n. But it's not important. What's important is this new temporal importance curve actually. So the temporal importance curve, even though the name might be intimidating, it's just a graphical representation as to show how particular features, how particular, how to explain this? Right. So the temporal importance curve will basically show you on the basis of the features which you're using. What particular feature of the time series interval or the time series data is actually being used to make the classification, or which particular feature is proving to be more important than other features. So the importance. So if we consider, as I said, we're in fact actually considering which feature is more important or plays a more pivotal role in classifying the time series data. So the importance K. So K is basically the index for, or just a variable which represents the feature type. So K in our scenario will be from 1, it will range from 1 to 3. And so for at the time instance T, or for example, at the T equal to 500 milliseconds, if you want to compute the importance of classifying the time series data at time series using feature K at suppose 500 milliseconds. So that importance of feature K calculated using the entity, the sum of all entities. Anyway, I really apologize for that.
Yeah. Can you
Yeah.
take it from the start? Importance key of time.
So basically, the temporal importance is just a graphical representation which will show you that for, okay, I guess using the graphs will be better as well. Right. So if we consider these graphs, so this particular graph is just showcasing to me or showing to me that at suppose which time instance, which particular feature is playing a more important role in classifying the input time series into the respective classes. So therefore, I can say that in the interval 200 to 400 of the input time series data, the slope of the time series data, the mean. So the slope and the mean play a much more pivotal role in the time interval 200 to 400 to classify the input time series data into one of the classes. Whereas in the intervals, for example, I think 450 to 620. So in that interval, the standard deviation of the input sequence. So that plays a much more pivotal role in classifying the input time series data into respective classes. So these temporal importance curves, it's just a tool or just a way to interpret what aspects of the time series data are actually being considered to classify them into respective classes. So this is sort of explaining the black box of the random forest how it's taken decision. So similarly, so this graph is just a distribution graph of the time series data. So you can see that the in the interval of 200 to 400, the mean of the value. So again, bi was, as I said, was the value of the time series at time I. So over here, as you can see that for class 1, which is pink in color, the mean is lower than the green region. So that's why in the interval 200 to 400, the temporal importance curve has understood, like, or has detected that the mean and the slope, right? The mean and the slope play a much important role. And whereas over here, it has picked up that in the region of 400 to 650, the standard deviation, it's varying a lot. Like the mean will be the same because of the time series data is varying in the positive y and the negative y direction. It's more or less going to be the same. But the standard deviation is very high. So that is going to play an important role. So similarly, this is the temporal importance curve for another kind of data set or another distribution of time series data. So I'll just go back to the formula, how to compute these temporal importance curves. Oh, and suppose this is the control group sort of, where, for example, if all our classes are exactly the same, the distribution, the mean and the variance of our classes are exactly the same. So what's going to happen is our temporal importance curve is sort of going to look like this. And if you are wondering why is there a peak in the middle, like even though there's nothing specific to classify down, there's a peak in the middle because according to the formula which I'll explain above, we, as I said, suppose I'm going to consider classifying at interval, consider computing the importance of a particular feature at interval time point 500. So the time point 500 itself will in fact occur more frequently in the subintervals which we compute rather than suppose a timestamp 1000, because the timestamp 1000 will only occur in those intervals which are actually at the edge of the time series. For example, the timestamp 500 might, like, it will occur in the interval of 400 to 600, as well as 450 to 650, as well as 500 to 7. But the timestamp 1000 will only occur in the subinterval of 800 to 1000, nothing else. So that's why in the control group, there's just a peak across all the features in the middle region, because, or seemingly that, because it's just because the timestamps in the middle region occur much more frequently.
Like because the sampling the random sampling we have is Gaussian in nature. That's why the middle will be sampled more often.
Correct. Correct.
It will affect.
So that's went too far. Right. So this is the temporal importance formula. So importance importance of a particular feature k at timestamp t is defined as the sum of all the entropy gains in the interval which t1 and t2 are basically all the intervals which contain the timestamp t. For example, for 500, these intervals will be, for example, 400 to 600, 450 to 650, and 500 to 700. So these three are the intervals which will contain the timestamp 500. So we're going to consider the entropy gain for all these three intervals, and also at node V. So V belonging to Sn. So Sn is just the set of Sn means split nodes. So it basically implies that yeah, in V are those nodes in which these time point V are the set of Sn are the set of those nodes in which uh, with intervals which contain a timestamp 500 are being received as input. So that's just a very basic definition of what we use. I hope you guys understand. So we are then going to compute the sum of all the entropy gains at all the data nodes V, get as input intervals T1 to T2, where T1 and T2 contain the timestamp T. And we're going to compute this importance for feature K. So we can then compute importance at timestamp 500 for all such features. This is what has been done in the graph as well. For each and every timestamp, we're computing the temporal importance of all the features. For example, the mean, the standard deviation, the slope separately, and we're just plotting it simply, which is the temporal importance versus the time graph. Oh, and if you guys are wondering, so this graph is just the basically It's just a graph which represents the number of time intervals each timestamp is in. It just gives us a relative idea of how many. So as you can see, the time interval 500 is in the most number of intervals, whereas time interval 1000 and 0 are in the least number of sub. Right, and num of t. Just a minute. Yeah, num of t is the formula which is used to compute the number of intervals, the timestamp t, which is quite simple: t into m of t into m minus t plus 1. Right. So these represent that was just circling back to the limitation of instance-based classifiers. Instance-based classifiers will directly classify on the basis of similarity, like how similar is the input time series to, for example, time series belonging to class one. So it's just a simple similarity comparison or transductive in nature. Whereas here we can actually determine or actually explain what on what feature plays an important role of classifying the input time series data into different classes. So that's how time series forests and temporal importance curves tackle this kind of a limitation, which is prevalent in instance-based classifiers. Right, and these are just texts which are just the verbose form of my explanation. So I've explained more or less what these graphs are, and that's the only important part of it. Okay, right, great. You read the experimental setup of it. Right. So again, they are using the same features which we had defined, which is the mean, the standard deviation, and slope for all the experiments. And they're just going to perform a simple benchmark. So the benchmarking is done on a number of data sets, like lots of data sets. So as you can see, this entire list of data sets, these are all time series data sets. So they have done, this is just the table summary of each data set. For example, a 50 words dataset has time series of length 270, the number of training instances are 450 and testing instances are 455. And there are a total of 50 classes which the time series belonging to the 50 words dataset can be classified into. So on and so forth, they have benchmarked the time series forest on lots of dataset, as you can see. And here they are comparing the time series forest algorithm. Right. So you're also considering two different variations. So the time series forest algorithm using the entrance, which is the novel splitting criteria. Not the criteria, but the metric used to determine the splitting criteria. So they're using that, and they're also using TSF, in which the entropy, which is the plane entropy, which is the most commonly used metric for determining the splitting criteria and random forest. And they're also using other algorithms which were supposed in 2013, which is supposed to be the state of the art for low compute resources. So InterRF, I'm sorry, I forgot the name, what that algorithm was. And nearest neighbors using the Euclidean similarity measure. Then DTW using the best window. So these are again variations of the nearest neighbor algorithm using a dynamic time warp. So within the dynamic time warping algorithm itself, there are multiple variations. However, I will not dive into that right now.
What are the values in the table?
Yeah, the values are in fact actually the error rates. So they have given a summary at the bottom of the table. But as you can see, for example, for the fifth data set, the error in the classification is 0.2659. It's more, I think it's the least, oh no. So DTW best in, for example, for the 50 words data set has proved to be the best classifier for this particular data set. But at the end of it, so these are all the error rates of each data set. The error rates of each data set being computed using all these algorithms. And at the end of this table, so here they are basically they've computed the average rank of every algorithm. And you can see the higher, the lower the rank, the better. For example, rank number 1 is better. And the higher the rank, the worse it is. So 2.48, so which is the time series polished algorithm using the entrance method, which is the new metric which they propose. So that is quite, which is very, it's ranked quite high, which is if you consider 1 to be a high rank, 1 to be a high rank and 5 to be a low rank. So So that's why they, according to benchmarking, that benchmarking also reflects their theories, which is that the time series forest will explain very well with the entrance metric, but also at the same time, the time complexity is only linear. So we are almost so basically what is the implication of this is that time series forest is a very strong candidate model to be used on low compute devices, especially if you want to build smart watches to, for example, classify the health condition of the heart using the pulse data, or you want to build a weather monitoring uh, weather sensing chip, which can also classify as to what the weather would be like of the day, etc. So there are so that's why time series forest is quite an optimal candidate for using performing time series classification on remote or not remote on mobile low compute devices. And I think we're almost towards the end of it because these are just different methods as to how they're ranking. So I believe that's not quite. We have used different tests, like different ways. For example, the Wilcoxon signed rank test. So these are just ranking tests to determine which classifier has performed better using the results which they have tabulated. So, but the average rank for classifier for the time series forest classifier with the entrance gain metric was the highest, and that's it was the best. And the final graph which I wanted to explain was basically these separate individual blue lines which you all can see on the graph. These are in fact the error rates which have been plotted for all the different data sets which are testing the models on. And in this case, it's actually only for the time series forest algorithm. And it's for all the different data sets. The y-axis is basically the error rate, and the x-axis is basically the number of nodes in that tree. So you can see that in the like initially just for a small increase in the number of nodes of the tree, there's a drastic reduction in the error rate, which is quite desirable. But as soon as we approach the 100 mark, so further increase in the number of tree nodes does not really affect our error rates. So what this is trying to say that even for what basically this implies is that for quite a few number of nodes as well, like obviously the lesser the number of nodes you have in your tree, the more efficient your tree algorithm will be because it will have to do less number of splits. So the lesser the number of nodes which you have in the tree, you can observe the greatest reduction in the error. So which is also quite desirable. So you need not use trees which are themselves very large, which have for example 500 nodes, 600 nodes, etc. So that's redundant. You won't observe a huge improvement in performance. Right. So they also mentioned that the represented by the thicker red line. So that's the red line is just the average of all the error rates. So all the error rates across the different data sets. And that's sort of like the trend line. Right. The gunpoint and the Wapner time series are the two specific time series data which they are using ahead to plot the temporal importance curves, just to showcase how well their plot is performing. Right. So if we compare these graphs, so for example, for the gunpoint time series, if we consider class 1, so the standard deviation of, according to this, in the time interval 20 to 60, I'm not sure what's the unit of time. It can be seconds or milliseconds. But in a time interval of 20 to 60, the slope and the standard deviation is much more of an important factor in deciding in classifying the input time series. You can see that which is evident over here as well, because in this time interval, the slope, uh, slope and the standard deviation is varying a lot. But in fact, which is what is reflecting in both the input plots as well as the temporal importance curves, is that in this region, which is the 60 to 100 region, the slope and the standard deviation more or less stabilize. But what's suppose varying, like, okay, also, like, I need you guys to look at the pink lines belong to class one and the green dotted lines belong to class two. So for the pink lines, the mean is generally higher, whereas for the green lines, it's concentrated over here. So the mean is generally lower, in the 60 to 100 range. So that's why the 60 to 100 range, the mean plays a much more important role compared to standard deviation slope. And since these time series data are in fact sort of a mirror image, what is over here, the same mirror image of it is being observed over here. So that's why, again, in this region, the peaks for the standard deviation, the slope shoot up. And the mean plays much less of an important role in the interval 100 to 147 milliseconds. Now, over here, what for the vapor time series, even though you guys might be wondering, the variance of the time series values is a lot over here. In fact, the thing is that in this particular region, which is 20 to 60, all, like, both the input sequences, which is class one and class two, they exhibit the same variance. And by variance, like, just to, in simple language, how widely the data or the plots are varying. So it's more or less the same. So that's why the standard deviation. And okay, I'm interchanging between variance and the standard deviation. But keep in mind that the standard deviation is just the square root of the variance. So over here as well, the variance of the standard deviation is more or less the same in the interval of 20 to 60 for class 1 and class 2. And if you notice, like, for class 1, the positive variation is only up to suppose 11, and the positive variation of class 2 is only up to 12. And in the negative direction, it's only up to -2 for both the classes. So that's why the mean is also more or less the same. So that's why there is no particular distinguishing factor in the 20 to 60 interval. However, what's happening is that in the standard deviation is playing much more of an important role in this latter region, because it's not really clear from this graph. But what's happening is the green region is relatively much more spread out, like especially in the 100 to 130 region, 110 to 130 region. But the pink line, which is actually hidden behind the topmost green region. So so the pink lines are extremely concentrated in this particular region, this small region. That's why, one second, can I draw? Correct. So, is the drawing? Yeah. So in this particular region only, my pink lines are focused on. That's why, like, those who are familiar with statistics and everything and understand graphs, so the variance in that time region is very low for the pink lines or for class 1 lines. But if I consider class 2, yes, if I consider class 2, the variance exhibited by class 2 lines is much greater. It's sort of this larger, it's, my drawings may not reflect, like, may not be appropriate, but it's sort of this larger region, like they're more widespread. So width of the green lines is suppose 4, so the width of the pink lines is only approximately say 2. So that's why in this region the standard deviation is much more important. It's also being plotted and verified with the temporal importance curves for the wait for data. And yeah, that's about it. So this section on so this is just a section of computational complexity. So they're just saying that it's just reiterating whatever I've stated till now, but with one other parameter, which is lambda. So they're saying that for each data set where m is the time length of each time sequence, like time points. So lambda is basically, they're saying that out of m data points, are only going to randomly sample lambda m. So in our case, we are considered to sample only square root of m time points from a time sequence. But here, they're just making that a variable over here in this line, just to plot the graphs. So when you make it lambda as well, so so lambda, suppose the lower lambda, the lesser number of time points you're going to random, like not less, basically length of the subintervals which is sampled from the time series, the length is going to be less. It's only going to be lambda and lambda n. So suppose that we have n number of training instances. So in the case where data sets which are in fact more than 1000 training instances, so they're just considering lambda n times. So the lambda is basically this parameter is more or less going to be the same, or it's the same multiplier for m number of time points and n number of data instances. And they've plotted this in this last and final graph. Right. So I believe this is the last graph. However, so they're saying that these are the different data sets which they're exploring. And the computational time of TSF with regard to the time series length. So the x-axis is actually the multiplier, and this is the running time. So as you can see, the relationship between the number of the lambda value and the computational running time, it's actually linear. Like this, you might consider to be very weakly. It's okay. You can say very weakly linear, but it's if we just try to fit a small regression line, we will definitely obtain very high accuracies. And this is also very close to being linear. So this is just again a much more. This verifies that time series forests in fact have O of m time complexity across various data sets, and multiply of the number of examples. So basically, the greater the number of data instances which is used to train your model, then the more time it's going to take. So these are just, so that's the thing, right? The computation time depends on the length of every subinterval which you have, and it also depends upon a number of data instances or the number of sequences which you're going to send. So all these factors which logically determine how long your model is going to take to train or I think that's about it. Yeah, so again, they're just reiterating that TSF randomly samples O of M features from O of M square features, and thus makes the computational complexity linear in time. And again, they're just reiterating that it's an ensemble of trees, and it's not easy to understand, but with the help of temporal importance curve. Like without a temporal importance curve, it might as well would have been a black box. So, but the temporal importance curve helps us understand what's exactly actually going on. And I guess that's it. Yeah, that's it. That's any questions?
If anyone has any questions from the panel, we can take it up now. Okay. As I mentioned earlier, that they are sampling a subspace of m square number of features, and the lesser number of features they are selecting, we are getting good accuracies. But if we wish to use more number of features, then accuracy would even be better. So in the above diagram, so instead of stopping the graph at one, if that is greater than one, then we'll be sampling more number of features. So, was there an evaluation of how better this algorithm get? Because already at using the strategy, they are getting SOTA scores, but like how far they can push using all M square features. Was there an analysis of this?
Right. To be honest, I've had the same question, but unfortunately, I don't think the authors have plotted this. They have reported any such data in the same. So unless and until we do such kind of an analysis on our own, like which is actually considering implement this time series forest algorithm from scratch and consider all the features in the feature space. So I can't really say for sure because even the authors haven't documented anything.
That's something we could look into for sure.
Yeah.
Uh,
It can even be actually, it can even be future work also, like some sort of future work. Like I'm not, I think they might have maybe like skipped out on this. Honestly, this was when I read this paper for the first time, this same question popped into my head. And then the answer which might pop into my head that maybe just to maybe pitch their TSF model as a better model, they might have in purpose intentionally left out that part, but nothing I can't say for sure.
yeah. And in the above diagram, when they are mentioning TSF uh, in the do they mean that they're dropping out the margin part in that consideration? One sec.
In the
In the
table, which is
table,
there.
yeah. Yeah, yeah.
Right. So
We
in the
have
table,
TSF entrance and TSF entropy.
correct. So in TSF entrance, they are considering the margin as well. And in TSF entropy, they're only using the entropy metric without the margin. So as you correctly said, they're not considering the margin to break ties.
Okay, we can observe that it still performs pretty good. It gives us a rank of 2.86.
Yeah, yeah, that's true. Yeah.
All right. So for application based, how exactly we deploy these models and how much of a difference does it makes like using one algorithm, let's say DTW over this.
Right. So you might, for example, I was sort of exploring. What do I say? I was exploring these multiple algorithms, even which I listed earlier, which was RISE and Weasel. So I was exploring TSF, RISE, Weasel, and NNDTW on hard data set. So over there, what was observed was that even though TSF, first of all, it outperformed all the other models, but we keep the accuracy aside. TSF was not much of a computational burden. So from the application point of view, like even suppose when we went on to use when we tried to train the QnA models for much higher parameters. So the QnA model took a lot of time. Like there were certain instances that where it almost we did not finish the computation and we were not able to report that because it just did not seem feasible enough to run the TSF, sorry, the KN and DTW algorithm for that many parameters. However, so basically we had to unfortunately leave out that part of our analysis where the standard procedure would have required that we listed that form of analysis. Like what would have been the results we, for example, the number of neighbors, just an example, the number of neighbors was set to 500. So what would have been the scenario been at that time? But just because of the amount of time taken, we had to drop that computation. So I think if that's the question, that's what I've understood the question from the
Yeah, yeah.
application point of view. So is there, in general, just out of it, first of all, it just its accuracy blew out the others out of the park. And yeah, it took much less time.
If you can you
Back,
explain to us? Yeah, go ahead, Sunny.
yeah, so I was saying that in fact, if I remember correctly, I think RISE. So RISE is in fact a modification of the TSF model algorithm, but instead of using statistical features for each interval, it's going to calculate spectral features. So by spectral features, so time series data can actually be considered in two domains. So time series data, as the name implies, can be considered along the time domain and can even be considered along the frequency domain. So RISE considered implementing a similar algorithm using frequency or spectral features. So there the features were, for example, the autocorrelation function, the spectral power, and the partial autocorrelation function, etc. So yeah, and it achieved similar accuracy, but because those features were inherently difficult to compute, so TSF took much lesser time compared to RISE and also higher accuracy. But RISE did report very close accuracies and slightly longer time.
Okay.
You were saying something?
Yeah, I was asking if you can tell us, share with us, can you tell what exactly you're working on and what kind of data it is and how these different models you're working with, what was the end goal of the project?
Right. Unfortunately, like I'm actually working on this with a senior, and the thing is, we are sort of in the purpose, like we're hoping that we might just be able to get it published. I'm not sure how much I can reveal, but yeah, as I said earlier, like for this particular paper which we were trying out, our end goal was to basically benchmark like different. Our hope was to actually produce results such that what we can we want to build a portable this thing portable heart disease classifier, which suppose you can wear it on your hand or something. And how which algorithm? So you were just benchmarking different algorithms. So the algorithms which I listed earlier, which I explained earlier about RISE, Weasel, TSF, and KNDW. So what we did, we got ECG data. So ECG again, which is heart data, it stands for electrocardiogram. So this is also an application of time series classification to healthcare. So in that case, what we're doing is that we again benchmark these algorithms across these different algorithms on our hard data set, and we're just sort of reporting scores. So that was just a very basic project.
So we are able to get ECG data through a smartwatch, you mean, or like through a watch which can collect data for heart.
Ideally, I mean, you can. Unfortunately, we do not have the hardware, so we're just monitoring. Our aim was to just tackle the software aspects of it, not the hardware. But like for example, you do get pulse meters and everything. So suppose if someone is in fact able to build a device somewhere where you can plug in a USB port into your smartwatch and extract that data, or better yet, wirelessly just send the data from the walls to our servers over the internet. So we can definitely collect ECG data. So yeah, that's possible.
Okay, I think that was all for the question sides. Do you have anything to conclude the session?
Not really. I mean, I hope you guys understood, because I realized there was a lot of disturbance on my end, and I actually hope that you guys found this session useful. Like, because time series, I also believe that at least in our college as well, it's not really much explored upon. Like many people usually venture into the much more popular domains of computation and NLP. So hopefully, I hope people are just a little bit more motivated to explore time series as well.
Definitely, this was a very inspiring peek through in the domain of time series, and we expect it very good how we are going through how the different algorithms work and what TSF actually works. Like even the mathematical explanation of it was perfectly clear for most of all of the parts.
Thank you.
All right, then with this we'll end the session. Thank you again for joining.
Hi, Sahil.
Yeah, sure,
Am I
sure.
audible?
Yeah, actually.
Uh, Hi, Sean. Thank you for the presentation. It was really helpful.
Thank you.
Yeah, I had a question, if that's okay.
Yeah, sure.
Yeah, I had a question on the DTW algorithm as such. I think it was the Medium blog post that you shared, where you explained where the algorithm was explained, the pseudo algorithm, and you actually try to go through like for the first one, in the first for loop you go through till n, and then you in the second for loop you go to till m, right? So but in the diagram you actually you know you kind of give a one-on-one correspondence, right? I'm not sure if I think the diagram is right there if you scroll down.
Sam, can you just scroll a bit up? I think that's
scroll a bit up. Yeah, this one. Yeah, you're actually doing a one-on-one matching between the red and blue lines, right? Both of these. And while in dynamic time warping, what you're trying to do is you're trying to do it in a different time interval as such. Am I right? Yeah. And the question was that the thing is that when you're going through two for loops from for I1 to M and for J1 to N, so how do you actually achieve this single one-on-one matching, right? Because you're trying to have an O of N square time complexity, if that makes sense.
Look, I think I get what your question is. So you're just asking me, like, using the algorithm which was displayed, how is this kind of a one-on-one mapping being
correct?
used?
Yeah.
Right. So I don't. Okay. So I like this. What I have understood from this algorithm and this explanation is that this first of all, just talking about this diagram, this is just a representation. It's just a representative diagram. So in fact, what is actually happening is, like, I'm not sure. Can I draw on this? No, I can't. Okay. Anyway, so what's basically happening is we're considering the. Okay, I'll just clarify one thing, that the final dynamic programming based approach which we're using in computing DTW. So over there, what's happening is we aren't really storing the mapping, the one-on-one correspondence between which data point has been mapped to which data. It's just that over here, this diagram is representing that if suppose I consider that we're traversing the red line using the I loop and the blue line using the J loop. So it's just traversing that for the first red line over here for I. Let's say that it has in fact calculated a distance metric across all these time points. And then it found out that the cost is basically minimum for these this corresponding point over here. So next, similarly, when we move on to the next point for I equal to 2, I equal to 2 would be then be compared from j equal to 1 to m. So all these points. And then you're going to calculate the corresponding point over which you have the minimum cost. So in such a manner, what will be the end goal? The end goal is basically it's going to calculate a final similarity score. The similarity score might just be 100 for these two time sequences. So if we just consider 100 as an individual number, it might seem very high. But if we were to suppose consider the Euclidean matching algorithm, which is corresponding, if this tells us something like 500, so at least DTW in that scenario is telling us that yes, these two time sequences are similar, which is actually being falsely represented using the Euclidean matching algorithm. So I guess does that answer your question?
Okay, yeah, I think I do get it. So in that diagram, if I have the red line, let's say at I is equal to 1, at I is equal to 10, let's say, and then that gets mapped to some j is equal to 25. So you get zigzag lines across each and every across both of these time series lines, right? Is that even possible? Like, because the cost would, what I'm trying to say is that the cost between one point on the red line could mean another a way different point on the blue line.
Yeah, so that's also true. I actually, while explaining this algorithm right now, also like the same thought, in fact, just popped into my head. Unfortunately, I don't think I have the answer to it. For example, I think what you're saying is that if we have two similar peaks, for example, one peak over here and a similar peak like this over. Oh, one second, can you just open the Jamboard? Yeah, I'll draw on my side as well. Right, just a minute. Yeah, so can you see my drawing over here?
I think it'll take some.
I see a blank screen. I mean, the a white page.
Yeah,
I can see the drawing now.
I think there's a latency. Yeah. Anyway, so I think what you're saying is that if suppose right, so can I change the color? I'm not sure, like I'm very new to this, but anyway, so we consider the point over here, and so technically, I think what I've understood is, which this thought popped into my head right now also. So for j equal to suppose 20 and j equal to this value, sorry for that. So I think just the distance metric, like I think you're saying that the cost might just be similar. Like it might think that this is similar to this. Is that what you're trying to say?
Yeah, exactly.
Yeah. So I think I must say that I haven't really explored that algorithm in detail. Like I haven't really went in that algorithm step by step. But maybe since it was a dynamic programming approach, and initially what was happening is that it's in fact initializing all the elements of that matrix to infinity and only the first element to 0. So maybe that somehow plays a role. I'm just speculating as well. I'll have to sit and actually do solve that algorithm. My competitive is very weak, but I think that role maybe the matrix at this point, we're considering comparing I equal to 10 and finding the corresponding values over here. Maybe the matrix at this point, the values would have been initialized as such by now, such that it would automatically. There's also criteria in the algorithm which it's actually taking in the minimum of three predefined three not predefined, but three different values in the matrix plus the distance metric. So they are actually updating the cost algorithm that way. So I think, like I'm just speculating around, but maybe this minimum part plays an important role in deciding which would be a better corresponding point. But I can't answer your question. This part with shortly.
Okay, makes sense. Thank you.
Sai, are you saying something? I can't.
Not really. I think we are towards the end of the session. Okay. Thank you so much for taking time and presenting your paper and dealing with all our doubts in a very. We'll get
My
back.
paper, but yeah.
Yeah. Sorry. The paper of your interest.
Yeah.
And we'll definitely look into the algorithm and see to it that we are able to understand what how it actually takes care. I think there should be some heuristic they are
Yeah.
applying in a way to avoid the nature or like to have some consistency throughout the mapping if we have. Uh, so we'll look into that definitely post session.
Yeah, in
And
hindsight, I should have to. Yeah.
yeah. Okay. Thank you everyone for joining. It was a pleasure. I'll end the stream on that.